Hello, it's Stat 134, Lecture 26. The last two times we did a lot of things. Back on Wednesday, we covered section 4.5, talking about the CDF. The CDF is the probability that t is less than or equal to t. This can be useful for example, finding the distribution of a min or max. If xi is independent exponential lambda i's, and m is the min of x1 to xmn, and you want to know what's the distribution of m, you see min, then you think to yourself, oh, I'm going to use the CDF. The probability that m is greater than t is the probability that x1 is greater than t, x2 is greater than t, and so on for t greater than 0. Independence tells me we have a factorization. I know the survival function, and product of exponentials here I can see easily that m is exponential lambda 1 plus lambda 2 up to lambda n. This makes sense. It makes sense that because as I'm adding up these rates, I'm getting a larger rate, which means a shorter time to arrival, and m is the min of arrival times for x1 to xn. We then covered MGF. So the MGF is the expectation of e to the tx. And so for example, if x takes values 1, 2, and 3 with probability 1/2, 1/3, 1/6, then the MGF is a sum of 3 terms. The number in front of the t is the value of x, and the coefficient of the e to the exponential part is the probability that x takes that value. So for example, just looking at e to the t times 1/2, I know that that x takes the value 1 with probability 1/2. We then looked at gamma. Gamma r lambda has moment generating function lambda over lambda minus t to the r for t less than lambda. Very, very, very useful. Today we're going to see that random variables with the same MGF have the same CDF. In other words, the MGF is unique, uniquely characterizes a random variable. We're going to review the concept test from Wednesday as well. We're going to learn how to use the CDF to find the expectation of x. So key properties of the MGF. If an MGF exists in an interval containing 0, then the kth derivative set equal to 0 is the kth moment. Super useful. Furthermore, if x and y are independent random variables, then the moment generating function of the sum of x and y is the product of the individual moment generating functions. This is proved in the MGF homework this week. And lastly, if two random variables have the same MGF for all t in some interval around 0, then they have the same distribution. In other words, they have the same CDF. And we're going to skip the proof of this. The proof involves the inverse of a Laplace transform, which is a topic in complex analysis. But you can see that property C here holds at least for when x takes a finite number of values. This is the example we talked about at the beginning. But it holds more generally. So property A is useful for finding the expectation of x and the variance of x. That's mainly how we'll be using it. Property B and C allow us to prove, for example, that the sum of independent Poisson is Poisson. So you did this proof here using moment generating functions. Very exciting. So x1 and x2 are Poisson mu1, mu2, and you're going to show that x1 plus x2 is Poisson mu1 plus mu2, a fact that we showed another way. So step one, you identify what the moment generating function is for Poisson, and you realize that it's exponential of e to the t mu1 minus mu1. And so you take two such moment generating functions, multiply them together, and you get e to the mu1 plus mu2 times, so all under the exponential times e to the t minus 1. And you recognize that, oh, this is the MGF of Poisson mu1 plus mu2. By the uniqueness of MGF, it uniquely specifies what the distribution is, namely Poisson mu1 plus mu2. So that's really the power of the MGF. If you're wondering how you go about proving, for example, the central limit theorem, guess what? You prove it using an MGF. Interested people, come see me about that. So we then talked about a review. We reviewed the concept test of the responses from last Wednesday. So remember, we were talking about leaving a party, time to leave a party. So if you walk to the exit, takes more than 1 minute, you run into a friend at the door and must spend the full 2 minutes to leave. Let t represent the time it takes you to leave. And you're asked whether the CDF on the right here is the CDF for t, and of course the answer is no. One student writes, the graph shouldn't start at 1/2. That would imply that half the probability is assigned to leaving at 0. It should start at 0 and increase uniformly to 1. Then there should be a constant line from t equals 1 to t less than 2, then a jump to 1 at t equals 2. Brilliant. Some not so perfect responses are in green. Other perfect responses are in yellow. I'll let you read that on your own. We then looked at the part 2 problem, and all I really want to say about that is that 66.7% of you got it right, and 53% of you said that the explanation for part 1 was helpful to you. So good job on working on those explanations. They're really important to help your classmates. So finally, we saw how to use the CDF to find the expectation of x. We first have to talk about the inverse distribution, f inverse u. So let x have CDF f of x. So let's show here first x being continuous. So notice that the CDF takes values between 0 and 1. Now if I randomly throw darts between 0 and 1, say u1, u2, u3 are IID uniform 0, 1, and I go to the curve and down, the fact is that I get x1, x2, x3, IID x. So that is very, very cool. That's actually a way that you can generate random numbers in any distribution you want, just using the CDF of that distribution. X doesn't have to be continuous. So for example, if x is a mixed distribution, as shown here, then this picture shows you how you would define f inverse u. So we have this theorem, let x have CDF f, then the random variable f inverse u is x. Totally awesome. Proofs at the end of the lecture. How's this useful to us to find the expectation of x? So take a look at this. The expectation of x is the expectation of f inverse u, because x is f inverse u. F inverse u is a function of u. U takes values between 0 and 1. So this is the integral from 0 to 1 of f inverse u. And then we have the density of u, which is just 1 since u is standard uniform. And that integral is exactly what's shown in green in this picture here. Here I'm drawing f inverse u, which is just a reflection around the diagonal of the CDF. And that, of course, if you reflect back across the diagonal, has this picture. So this is fantastic because to find this green area here, all I have to do is integrate 1 minus f of x from 0 to infinity. So that's this theorem here. Let x be a positive random variable with CDF x. The expectation of x is the integral from 0 to infinity of 1 minus f of x dx. This is the continuous analog of the tail sum formula, by the way. So you can see how easy this is to apply. Say that t is exponential lambda. We know it has CDF as shown. Calculate the expectation of t. Just follow the steps. It's so unbelievably easy. This is much easier if you revisit how we did that before. Much, much easier. We also can find the expected time to leave the party is 5/4 minutes. That's kind of interesting. We then did a concept test. So let x have density f of x equals x e to the minus x for x greater than 0. Find the MGF. So I've been trying to train you guys. When you look at a density, try and see whether it's it is a known density, or at least a variable part of something that you recognize. So here we recognize that this is gamma. We see that it's gamma r minus 1 e to the minus lambda x. I'll just say it's a variable part of this. So we know that x is gamma 2, 1. And we know that the MGF of gamma r lambda is lambda over lambda minus t to the r for t less than lambda. So the MGF is 1/1 minus t squared for t less than 1. A follow-up question. If I just give you the MGF, I want you to then recognize that, oh, this is the MGF of a gamma. Which gamma? I can tell because I know what the MGF is for any gamma. I can recognize that this is the MGF for r 1/2 lambda equals 1. So there you go. MGFs are an incredibly useful tool. I'll see you guys on Wednesday.